Okay. We are happy to have Professor Renan from Federal University of Rio Grande do Sul, and he's going to present something about mobile robotics, which is the third part of this lecture. And this professor, please feel free to start the presentation.
Okay, thank you, Enrique. Today I will continue the talks that I was talking yesterday about mobile robotics, which is what we do here in Porto Alegre, Brazil. Today I'll focus on two problems. The problem of SLAM, simultaneous localization and mapping, and integrated exploration, which is also called as active SLAM. These two problems, especially SLAM, is the main focus of our researchers in mobile robotics. Because in practice, one of the fundamental tasks that we need to solve is localization. As I showed yesterday, if we know the precise robot location, maybe we can perform mapping, that is, building a map based on the observations made during the motion. We can perform planning, which is to plan where the robot needs to go, plan the trajectory of the robot, and we can perform exploration. Okay, exploration is the combination of mapping and motion planning. Basically, is finding the best trajectory to build a map of the environment in the smallest time. In practice, we must consider an uncertainty in the localization, because all those three problems need a precise estimate of the robot position, but in practice we do not have that. So the odometry information is uncertain. The odometry is the estimate of the motion of the robot based on, for instance, the velocity of the wheels of a mobile robot, or maybe based on the variation of the angles of the joints of a humanoid robot, and this information is not precise. And the problem is that the error in the estimate of a relative motion is small. It's usually small. For instance, the error in the estimate of a robot that you say to move 1 meter, the error will be around a few centimeters. But the problem is that over time, those errors are accumulated, and so after some time, the pose estimate may be very wrong. And for this problem, we need to solve. We need to correct estimates, which is done in localization. If we do not consider this uncertainty and we build a map of the environment based on the odometry, the resulting map will be highly distorted. And here's an example of a map of a building here in the university with the robot that we have here, which is a robot with 2 wheels, and the odometer of this robot has a systematic error, but also some errors that we cannot we cannot prevent to occur. And map based on image on the top. We need to correct the estimates, to correct the estimate of the robot pose, and we do that solving this map. And the result of solving this map is a map as the one shown in the bottom of this slide. So the problems considering localization, uncertainty. Well, the first problem is localization. Localization is to estimate the robot pose based on the observations made by the robot in relation to a known map. And I talked about this problem yesterday. It was the last problem that I talked. And it is a quite difficult problem in comparison to mapping and motion planning. It is more difficult than the other 2 problems. If we combine localization with motion planning, so we plan the robot motion in a known map in order to improve localization, this problem is not that hard if you consider the localization technique as a black box. And the simultaneous localization mapping SLAM is the problem where we want to estimate the robot pose, estimate the localization, at the same time that we build a map. So we consider that the map is not known a priori, and this problem is very hard. And this is the problem that I will focus on this presentation. But the integrated exploration problem, or active SLAM, is when we combine the motion planning with SLAM. What we do usually is to plan a robot motion that improves SLAM. So we try to guide the robot to regions that are better to correct the map. And this is, once again, not that hard, such as active localization, given that the SLAM technique is done. We consider SLAM as a black box, so integrated exploration is not that hard. What is very hard is SLAM. So, talking about SLAM. SLAM is the acronym for simultaneous localization and mapping. It is a problem that has been studied since the beginning of the 90s. The concept of SLAM is to estimate the robot pose and the map at the same time. It's fundamental for truly autonomous robots. It's probably the most important task that an autonomous robot should perform. And we can say that it's a chicken or egg problem, because to build a map we need a precise localization. We need to know where the robot is. So based on the robot pose, we propagate the observations of the robot and build a map. The problem here is we do not have this localization, because to estimate the localization of the robot, we need a map. We need to compare what the robot is seeing to what our estimate should see in the map. So these two tasks depend on the other, and because of this is a very hard problem. Yesterday I presented the base filter, so today I will not repeat that. But the idea, the the main idea of the SLAM strategies is to use base filter, is to use this tool for a recursive state estimation. So the idea is to form always a prediction of the state of the system, where the state is the robot position and the map, and then correct this estimate using the observation made by the robot. And this is repeated at each instant. Okay, so I will pass this is the derivation of the base filter because I presented yesterday. But basically, the idea is always to update the state of the system based on motion model. So the robot moves, we know the action that the robot took. For instance, we know the velocities of the robot, the velocities of the wheels, and we can estimate the new state of the robot based on the previous state. This is done in the prediction step, and then we use the last observation made by the robot to update this prediction, to correct this prediction, using what we call the observation model. The first approach that was used to solve SLAM, it was proposed in the beginning, of the 90s. The use of this approach in SLAM is the Kalman filter. The Kalman filter is a technique. It's a quite old technique, but it's used for localization mapping. Only was proposed in the beginning of the 90s. But the idea of the Kalman filter is to implement the base filter, is to implement this strategy of prediction and correction. And to implement a base filter, we need to define a motion model and an observation model, and we need to define the distribution that we use to represent the state of the system. In a Kalman filter, this distribution is a Gaussian. So the position of the robot will be given by a mean and a variance. Or if we are working in 2D or 3D, we have a vector representing the mean of the state. For instance, the mean in X, Y, and Z, if it is in 3D. And the uncertainty will be represented by a covariance matrix. Okay. The Kalman filter also needs that the models, the motion model and the observation model must be linear models. Okay. So, an example of a linear model that we use in the Kalman filter is, well, first the example of the motion model. We have the current state of the robot that we want to estimate, xt. We say that xt is a combination of the previous state, xt minus 1, multiplied by a matrix AT that gives the evolution of the state without controls or noise. Usually this matrix AT is the identity, because we consider that the state does not evolve without the application of controls or noise in the environment. So we can say that the current state will be the previous state if AT is the identity, plus the application of the motion model. So BT is a transformation from the previous state to the current one, given the control applied in the current state. So this BT is where we define our motion model. And for instance, the motion model can be the transformation of the velocity applied in the problem, given the time between t and t1. And so this is the relative motion from the previous instant to the current instant. And this epsilon is a process noise, is a noise that we consider to appear in the system, is the noise of the motion of the problem. And usually it's a noise with zero mean and some covariance. Okay. So this is the motion model. The observation model is also a linear model that basically applies this CT. CT is a matrix that transforms the state of the robot into a estimate observation, an estimated observation. So let's suppose that the observation of the robot is a vector of readings, of distance readings obtained by a laser or by a sonar. Let's say that the robot reads eight measurements of a sonar in different angles. What this observation model does is to, given the robot pose and the map, because here we are considering that the map and the pose are represented in the state of the system, so are represented in the X. Given this state, we apply this observation model to predict what the robot should see. And then we apply some noise. This delta is a noise, once again, with a zero mean and some covariance, to estimate the observation. Okay. So the idea is to I'll not show the derivation of the Kalman filter, but we get this motion model and this observation model. We get the predictions, the belief and the correction that are Gaussians, and we apply those equations in these two equations of prediction and correction. So the motion model is a linear model, the belief is a Gaussian, and then we need to derive these equations to find the resultant equations, and this derivation is not trivial. Is not even near to be done in small time. So I'll just present the results of the derivation. So the derivation of the filter, you can check in the book of Sebastian Trum, Probabilistic Robotics, is something like 10 pages of derivation. But the resulting equations are this. In the prediction, we need to update the mean of the state of the system. The mean is the first equation. So we use for this the motion model here. BT applied to the control, to the action of the current state, and this sigma is the covariance. The covariance that represents the uncertainty of the estimate. So the prediction basically applies the motion model here, B. RT is just noise that we add. And if we consider that A is this state evolution matrix, and A is usually the identity. In the prediction step, what we do is to increase the uncertainty here. This term just maintain the previous uncertainty, and then we add some noise. While in the middle we just apply the motion model. This is the prediction. The correction is more complicated. But basically we correct the mean. So here's the mean that we just computed. And then we apply some correction based on the observation. ZT is the current observation, and this CT times mean, the previous estimate, is the estimated observation. So this is the real observation, and this is the estimated. So what the correction does is, based on some variable k, which is the Kalman gain that we call, we approximate the estimate of the state more, depending on k, more to the real observation or to the estimate based on the previous state. So, and k, how we compute k? K is based on the uncertainty that we have and the noise of the observation. Okay. If the noise of the observation is 0, for instance, if we know what the robot observes is precise, and then if this is 0, the Kalman gain, well, this term will be eliminated. Then we will cut these other terms, and the Kalman gain is the inverse of the observation model. If the observation model is CT, the Kalman gain will be the inverse of CT. Only if Q is 0. Okay. So what this means? If we know that the observation is precise, then we can consider that the Kalman gain is the inverse of the observation model. So we use directly the observation model to correct. Basically, we say that what we are observing right now is, let me say in another way, the best estimate that we have, considering that the robot is observing ZT, would be the exact position. So if this observation is precise, we apply directly this correction. But let's say that the uncertainty of the observation is quite high, then this term will, let's say QT is infinite. Okay, so this term here, the Kalman gain will tend to 0, and this term here is ignored. So if the uncertainty of the observation is high, the correction basically does not correct anything, and we keep the previous estimate. So this is the idea of the Kalman field. We have the prediction of the belief of the system. The prediction will give us a Gaussian. Then we perform a measurement, and usually the uncertainty of the measurement is much smaller. And with this measurement, we correct the belief. So if the uncertainty of the measurement was much smaller, the correction will tend to approximate the belief to the Gaussian of the measurement. Okay. Then we repeat these steps: prediction, correction, and always in the prediction we change the mean based on the motion, and we increase the uncertainty with this noise. So after prediction, the Gaussian will spread more in the state space. Then we perform another measurement, correct the belief, and do this repeatedly. The problem is, okay, this was the common filter presented in the 60s, but in practice we cannot define observation models and linear models using linear equations. Usually those models are non-linear. So what is made to solve SLAM is to linearize the functions, linearize the models. Let's say that the motion model is a function g and observation model is a function h. We linearize those models. And the problem is that one way of linearizing it, which is the way that we do, is using a Taylor expansion. I'll talk about it later, but the idea is that if we have a Gaussian distribution and our motion model, for instance, is linear, here is an example. We apply this Gaussian in a linear model and we obtain a Gaussian. But if this model is non-linear, we apply this Gaussian and obtain something that is not a Gaussian. But we need to use a Gaussian in the common filter. So what we do is linearize. We apply a Taylor expansion, then we use the derivative of the function applied in the mean of the Gaussian. And then we have an approximation of the Gaussian after the application of the models. And this is what is called extended common filter. So the first approach used in SLAM was the EKF SLAM, extended common filter SLAM. And the first implementation of this method was in the 90s, but the proposition was in the mid-80s. And in the EKF SLAM, the state is the robot pose and the pose of the objects in the map. Okay, so this is what we call X. And consider that we have n objects in the map. The dimension of this state will be in 2D, will be 3 plus 2n. Okay, so we have a Gaussian with this dimension, 3 plus 2n. So here's an example of mapping using objects detected in the environment. So each one of these crosses are objects, and here's the robot position. So basically the state has a covariance for each of these objects, and as the robot moves, we update these beliefs. An important thing in SLAM is that when the robot closes a loop, which means when the robot returns to a region that was already observed, the robot can decrease the uncertainty of the system as a whole. And so loop closures means recognizing an already mapped area. This is how we collapse the uncertainty, and this is one of the main points that we will explore in active SLAM in integrated exploration. Okay, so now I'll show an example of the common filter. Let me see. This is one of the first implementations of SLAM. Here the objects are trees detected in the environment, and the experiment was made with a car moving in the environment, detecting these trees. And the idea was to determine the localization of the robot and the localization of those objects at the same time using an extended Kalman filter. So these are slides from Sebastian Trump. Just a minute that I need to talk here. Okay, sorry. Let's go back. So, here's an example of the car moving in the environment, detecting the trees, and this ellipse is the uncertainty of the vehicle. And as the robot moves, this ellipse will grow or shrink depending when the robot returns to known regions. That is when the robot closes loops. And so this is an example of the Kalman filter, which is the same. In the end, the resulting map is something like that. So we have a trajectory of the robot and the position of each object in the environment. Okay. Kalman filter was the first one solution. The problem is that the Kalman filter is not that good for large environments because it has some quadratic cost in the number of landmarks because we are performing operations with matrices and we are performing inversion matrices. And this is after some time when we work with lots of objects, this becomes costly. But it is successful in medium scale scenes. But the main problem is that require Gaussian distributions, and this is not that good when we are working with robots because the motion, the motion model, the observation model are not linear, so we are performing approximations, and even the estimate of the robot position is not a Gaussian. But it's a good approach, and it is used even today, depending on the size of the problem. But what is the state of the art in SLAM are graph-based approaches. Are approaches that use a graph to represent the problem. So, in this graph, the nodes of the graph represent robot poses, and the edges are constraints between those nodes, and these constraints can be obtained based on odometry and based on observation. This is the important point. So, the constraint between a node generated in instant t-1 and the node generated in time t is a constraint based on odometry. We know we have some error given by the odometry, but the error is quite small, and we know, for instance, if the robot moved 1 meter from time t minus 1 to time t, we can say that this is a good approximation, a good constraint that we can apply between the node in time t minus 1 and time t. Nodes based on observation are generated when we close loops, when we detect that we are observing something that was already observed in the past. So, in the example here, at time 7, the robot observes the same things that were observed at time 2 and time 3. And then we can connect those nodes with constraints based on observation. And the idea of graph-based design is that when we generate those constraints, we will have differences in what are the errors in the positions of the graph based on odometry and the errors as observed by its sensors, the errors given by the constraints made by observations. So, and the idea is that, so here in the bottom, on the left we have a graph of an environment where we have lots of black lines here that are constraints made by observations. All the other nodes are generated based on odometry. The idea is to reduce the errors of both odometry and observation based constraints and obtain an optimized graph. Okay, and this approach of graph-based design became popular in about the last decade, and it is what we do today. Graph-based Islam systems are composed of two parts. We have a front end and a back end. The front end is where we build the graph, is where we find the associations between nodes, where we generate constraints based on observation and based on odometry. At front end, we need to perform place recognition, we need to detect loop closures, and to do this, we will use matching techniques, comparing the observations made by the robot. And here depends on the sensors, based on the sensors that the robot has. And today, what is most used are cameras. So we use techniques from computer vision to detect matches between images and detect that the robot returned to a known region. This is the role of the front end. And the back end is where we optimize the graph. So here enters the techniques of graph theory and the graph optimization. Usually we deal with a nonlinear least squares optimization problem, so there are lots of techniques to solve this optimization. And using this approach, we can separate the front end from the back end. So lots of researchers focus only on front end, and while others focus on back end. Here we focus more on the front end. Okay. So the basic idea of graph-based design, here is an example. This would be the initial map built using only odometry, right? But when we find the constraints based on the observations made by the robot, we build a graph considering these constraints. So here, the black lines are the constraints that we found. And the idea is to find a node configuration that minimizes these errors, optimize this graph, find the correction of this graph, and then we can render our map based on the correct poses Okay, so we can project the observations using the proper estimate of the position of the problem. And this is what is done today in SLAM. So there are 2 points: how to optimize the graph, and then the complementary point is how to build the graph. How to optimize the graph is the role of the backend. It is an optimization problem, so here's an example of what we want to do. Is that for each edge in the graph, each edge connecting 2 nodes, we have an estimate of the transformation between those nodes. Is the displacement between that the robot made between those nodes, and we have the distance between those nodes that are defined in the graph. So, for instance, it would be the distance between those nodes given by the sum of the odometry displacements. This could be the distance that we have in the graph, while we can have the observed displacement that we found by closing loops. So the error is the difference between those two displacements, the observed and the estimated. And the goal of the optimization is to minimize the square error, the sum of the square error of each edge in the graph. Okay. An important point is that each edge has an uncertainty, and here is this information matrix, which is the inverse of the covariance here, this omega, and we use this to weight the contribution of an edge in the minimization. For instance, if the uncertainty is too high, this edge would be not that important during the optimization phase. Okay. The most popular technique for optimization is solve least squares using Gauss-Newton. I will not enter in details, but the steps are to, well, we have the errors, the equations of the errors here. We want to minimize this equation, so first we need to linearize the errors, compute the sum of those errors, and to find the minimum, to find the result that minimizes these errors, we compute the first derivative, set it to 0, and solve a linear system. And then we obtain a new state that we are hoping that is closer to the minimum and iterate into convergence. So this is a problem that is solved in a numerical way. Basically here is the steps. First we have the error function. We need to linearize this error function, so we perform once again a Taylor expansion like in the common field.